Hello everyone, welcome to the 13th tutorial of the Functional Data Structures course. Today I'll be doing some exercise related to amortized complexity analysis of running time complexity, amortized analysis of running time complexity. But before that, I would like to just say a few notes. So firstly, for the Be Creative homeworks, I've received a lot of emails and I tried to respond to as many of them as possible, but unfortunately some of them I missed. But in any case, it seems like there are a lot of interesting projects. So if any of you would like to present your projects, you can just send me a 5 to 10 minute video in which you present your project, and then I will compile these videos into one longer video maybe and put it with the next tutorial. And in those videos, all of the like some of the projects or however many of the projects you want to explain will be explained. Okay. Because I think some of them are interesting and maybe other students would be interested to know what everyone else did. Secondly, I just want to confirm that in the exam it will just be like the homework basically, in the sense that we'll use the contest system, and the exam questions will be answered. You will download the submission file and then edit it and then upload it. But you will also need to send me an email with your answers in it. Okay, so your answers have to be an attachment. So in addition to uploading, you also need to send an email just to make sure that that you didn't the uploading maybe, for example, would not work on time or something. So just do both. Okay. So now we'll be doing the exercise about amortized complexity analysis of operations on a stack that supports a multi-pop, which is basically a pop operation that takes a natural number and then pops as many elements from the top of the stack as the number is. But before I do that, I will recap with you amortized complexity analysis. Okay. So first of all, assume that you have a data structure, let's say D. Okay, and then of type D. So this is, for example, a stack or a list or something. Okay. Okay. So now you have this data structure D, and then you, for example, have this multi-pop operation on it. Okay. So we can say we know that the worst case analysis. So this pop takes like a number, natural number n. And that's it. So you pop the n elements from this D. Okay. So the worst case running time for this pop will be in linear in n. Okay, because we just the stack is implemented as a list, and then we're removing the first n members of the list if there are n members. Okay. So this is the worst. So this is the worst case running time for each invocation of the operation pop or this multi-pop. Okay, but there is a different kind of analysis that is more fine-grained than this worst case analysis. Okay, and that is suppose we have like a pop, like an operation 0 and an operation 1 and then an operation 2, etc. and then an operation n-1, for instance. Okay, so we do all of these pop operations or operations in general in our data structure. Okay, and each one of those takes a running time t node, t1, t2, tn-1. So each one of those operations runs in that time, in that actual time, not just worst case running time. Okay, so we can do a better analysis than the worst case analysis that we did here by the following. Okay, if we know that, for example, the sum of t naught, t1, t2 until tn minus 1, if we know that this is like, so this summation is less than or equal is in on, for example, okay, and then we did n operations, we know then that each one of those operations, so there might be one of them that actually runs in on, but the other ones must run in something that is less than on, okay, and that gives you more insight into the complexity of the operation. Okay, so so let me summarize again. So this one is the worst case running time for a pop, for instance. Okay, but not all of the pop operations will be that bad. Okay, so I here actually forgot something. So this, let's say you're trying to pop n elements, and this n is the size of the of D, the stack. Okay, so here the worst case running time is upper bounded by that, but we also know that the worst case running time of this sum will be upper bounded by not n but by the something linear in the size of D. Okay, so so now let me try and be more and go more towards the actual analysis. So as I was saying, the goal is to get something that around the summation of the running times of each of a sequence of operations. Okay, and that summation and you hope that this summation is still it gives you an indication that each one of those operations, if run within a long sequence of operations, is better than the worst case running time. Okay, so now what we're trying to do is to come up with some amortized cost, some just number, let's just call it AI, okay, for each of those operations. So we want A0, A1, A2, an minus 1, okay, such that the summation of these AIs is greater than the summation of TI. Okay, we want to come up with an AI, an estimate AI that has this property, so that when you sum these AIs over a long sequence of operations, you get an upper bound over the actual running time of this sequence of operations. Okay, so one way to one such AI can be devised as follows. So we identify a potential function that maps our data structure. I'll just say whatever, D for instance, and it maps it to a natural number. Okay, so we identify that function, and then we say that, so here for example the state of the data is D0, of the data structure is D0, D1, D2, and then Dn minus 1. Okay, this is the state of the data structure. Okay, and we can just say that AI, for instance, we will just define it to be Ti plus the potential at Di minus the potential at Di minus 1. Okay, I'm just defining that. Okay, I still didn't say why does this make sense to be an amortized cost. Okay, so now you can just follow the proof in the lecture. It's a very simple proof, and in that proof you basically say if we define AI to be like that, then it will achieve the property that the sum of this Ti is upper bounded by the sum of AI. Okay, so now we know that if we do a sequence of operations on D, then the cost of each of those operations will be AI. Okay, the amortized cost of each of those operations will be AI. Okay, so maybe I can just, maybe it would make sense to quickly prove that. I don't really know. Yeah, I'll just quickly prove it. So basically, okay, so we want to show that this AI is the amortized cost. Okay, so and what that question means, does this inequality hold? Okay, so I will just prove it, and it's a simple proof. So we know that the summation of Ti equals the summation of AI. Of course, I'm not going to write the starting and the initial and last index here. The summation, I hope it's clear from the context. Plus 5 of d of I minus 1 minus the potential of Ti. Okay, and that follows just from the definition of AI. Okay, and then we know that this is equal to the summation of AI separately plus the summation of di minus 1 minus di, and that is the same as the summation of AI plus the potential at the initial state of the data structure minus the potential at I'll just say, d like n minus 1, which is the final one there. Okay, and okay, so we I stated that this potential function maps the state of the data structure to a natural number. That's the first constraint on it. And actually, in order for this to hold, in order for this inequality to hold, we want this thing to be less than or equal to 0. Okay, and the only case in which this is less than or equal to 0 is that this potential at the initial state is 0, and the potential at any I is greater than or equal to 0. So if if these two constraints also hold, then this can help us. This can lead us to the conclusion that this summation of TIs is less than or equal than the summation of the amortized costs, and accordingly the sum of those AIs is actually an upper bound on the real running time. Okay, and it also is an indication of the running time of one operation in the middle of a long sequence of operations. Okay, I'm not saying it is exactly the running time of one operation, but it is an indication of the actual running time. Okay, so it's not like I just want you to note that this is not the average running time. This is not this is called the amortized running time, and it's an indicator of the running time of each one of the operations in the middle of a long sequence, in the sense that the sum of those amortized running times is the actual running time. So the sum is the actual running time, but each one individually is just an indication of the running time of one process, of one operation, but it's not the average. For instance, it's not it's its own thing. Okay, so now let's start doing this for our stack, so I'll just copy the definitions for the stack, and then we want to do this analysis. So I'm just replacing the okay, so these are just the things that we were doing there. Now let us change this to push. So now this is the actual running time of the operation, which is equivalent to TI on the notebook there. Okay, and so basically we have two operations, and then we want to analyze the like if you have a sequence of push operations, okay, just push operations, a sequence of push operations, what is the amortized running time of each one of those push operations? Okay, so we start the analysis as I was just describing by devising a potential function that is initially 0 and that is always greater than 0 after the initial state of the data structure. So I will just say, let's say definition so phi of, so it takes the state there. Okay, and I will just say it returns the length of that list and try. But it really you really have to. This is where all the work goes, basically selecting this potential function. Okay, we want to select it such that we show that so the challenge is to find a constant such that this amortized running time is equal to that constant. So we know what TI is because this is tpop, for instance, for the pop operation, and we're trying to find a potential function such that the amortized running time, which is t plus that minus that equal to some constant. That is the question. Okay, so use the potential method to show that the amortized complexity of push and pop is constant. So the goal is, let's even not define that. Let's just say this is equal to 0. Okay, and just find the goal. Okay, lemma. The goal is to say that t pop of n plus the potential sorry, this is for push. Okay, push just one element, and then here we have the new stack, okay, which will be push x into the stack, and you subtract from that this. We want this to be equal to some constant c, okay? So I will just say that this C, for instance, well, let's firstly, before identifying the C, I will just say this is the length of the stack, and then what constant should that be? I mean, one way to identify that. Okay, so actually it does tell us here that in the counterexample, it told us that if you put C to 0, this will not work because C will be 2. So let us just try 2 and see what happens. And then induction, access, auto. Okay, it doesn't work. So, yeah, because we need to unfold the definition of the potential function. Yeah, so now we have T push. And what is T push? T push definition. Yeah, so we have that. Okay, so now we know that the amortized running time of each operation is 2. Okay, of each push operation in a sequence of push operations is 2. Now we have pop as well, so the pop operation. Okay, so this is just push. I'll just use this as the 1 for push. And then the 1 for pop. I'll also use the same one actually and try what it will be. So you have pop, and then if you pop n of those n elements from that phi, from that x's, what is that? Okay. Okay, and now what does it say? So this actually can be 0. So let's see that tpop def. Yeah, that works. And the reason I said that, okay, here the counterexample that Isabelle gives you suggests you the constant, which is the cost of each of the running, which is the amortized cost of each of the operations. Okay. So I think that's it for today. It was a short tutorial, so I hope I wish you all the best of luck studying for the exam and practicing your Isabelle skills and sharpening them. And that's it for today. Thank you.